Hi everyone, I am Matteo.
And David Mops.
We are here to talk today about a new way to profile Node.js. You can follow along the talk. It's over there.
nf.ie/a new way.
And we both work for Nearfirm. We are a Node.js professional services company.
We're hiring.
We are hiring, yeah. We are also companies all over the world deploying fantastic JavaScript applications. So hey, if you need help, just call us. So
I love how big this screen is. It's really. Yes. Don't worry, that you shouldn't be blind to too much. We've got nice, calm colors.
So
and hot pink.
This talk is about performance. It's big, and both myself and Dave have been traveling the world over the last 3 years, 3.5 years, whatever, something like that. Traveling between companies, helping them solving their performance problem on Node.js.
And we've also built, from that, we've built tools, libraries, built like a cool fast logger, and we've been on a journey. Matteo and I have been on a journey. In fact, you could call it a perf romance. How cool is it? Yeah, right? And whether it's performance, whether it's romance, anything you take for granted, the words of the Counting Crows ring true. Don't it always seem to go that you don't know what you got till it's gone?
Because one day your phone will ring. Sales traffic is dropping down. You have a performance problem in production. Things are going down. And angry people are angry. And you have pitchforks going on Twitter. And
So what do you do?
Oh, well, everything. When your computer is not working, what you do, you reboot it, whatever. You add more servers, buy more machine, throw some money at it, and it just came back. Everything comes back online. It was not so drastic, right? I was called in on a Saturday morning. But that was not nice. But that's what you do. But after the big problem, there is a very important question that everybody asks themselves: why is it slow?
Because bottleneck, which isn't proper English, but we felt that was the best way to describe what we're trying to say. So a bottleneck is any part of a system that is the slowest part of that system. And when it comes to finding what the bottleneck is, it may be internal or external. If the bottleneck is internal, your Node.js process is on fire. And if anyone looked at the agenda last week, the name of this talk would have been "Help My Node.js Processor on Fire." But if the bottleneck is external, then something else is on fire. So what we want to show you in this talk is not only how to find internal bottlenecks, but something that we've put together to show how you can find external bottlenecks by profiling a Node.js process. So the question then becomes, not why is it slow, but where is the bottleneck? Because that's the question that will lead you down a path.
So this is a nice story about how you fix a performance issue. So first of all, you are in production, right? And things are not going well, whatever, you had a problem. You need to have some diagnostics in place already so that you can understand what that was the problem. So you can use CloudWatch, you can use an APM, application performance monitoring, a lot of different techniques to actually gather some diagnostics data. This diagnostics data is typically coarse-grained and very polluted. So there's a lot of other things happening, a lot of different users interacting with your application. So you might want to, it's hard to understand exactly what's happening most of the time. So what you do is the next step is reproduce the same problem you are having on a production-like environment that's not live. You want to reproduce it in the lab so that you can actually fix the problem, right? But it's still deployed, it's still a staging environment, you can call it the way you want. The way you do this, typically for web apps, is you simulate load. And we wrote this nice little library called AutoCannon, which is a JavaScript module, npm install AutoCannon, hey, No C dependencies, no nothing. And it also works on Windows very well, very easy to install. And the way you use this is you can script it with JavaScript as well. So a lot of you maybe use AB or WRK or JMeter or something like that. And you can do this with Java, with Lua and other things. You can do this with JavaScript and Node. It's nice and easy to use. So you can try this out. So after you simulate some load, you can reproduce it on a staging environment. Then, but you don't really work on a staging environment. How many of you have tried to code on a staging environment live, trying to fix a problem? Like, it's not really easy. It's not
or recommended.
Or recommended, no, not at all. So what you want to work on your local development machine. So what you want to use, you want to use some data from these systems that you have set up that you were able to use to reproduce the problem to actually be able to do it on your machine, on your developer box. And then you have some, you can,
Oh, shoot.
Man.
Sorry.
Dang.
I was trying to get the cursor off the screen.
Okay.
We're good.
What you do is you have some fine-grained, you can use some fine-grained, once it's on your development machine, you can use some fine-grained diagnostics that is also very clean. That's also completely unsuitable for production usage at all. But then there is the magical where the magic happens. Okay, so at the beginning, I started staring at the screen for a long time, days long, like, Then I upgraded my gear. I got a dog. So I started walking the dog. The dog loves walking, so it's fine. Dave, what do you do?
Oh, I like to take long showers.
Yeah, okay, you see? It's nothing related to coding. And after this, after the magical step, you fix the problem, and you get a performant application.
And so something that we've been working on in Nearform is making these final steps easier. So instead of staring at the screen for a long time, we want to try to make that information easier to understand, easier to read as a human. So what we've been creating is something called Node Clinic. So Node Clinic can be installed just as an NPM dependency, and it's a banner a repository or banner package for 3 tools: Clinic Doctor, Clinic BubbleProf, and Clinic Flame. I'm going to talk about these tools, I'm going to demo these tools. So tell us about Clinic Doctor, Teo.
So Clinic Doctor injects some probes into your Node.js process. And in order to assess and then you hit it with some load, with autocannon or whatever you want to use. And then it uses this probe to assess the health of your process. Now, the way we have developed this, so before this tool, I typically did that by generating some various different diagrams and graphs, matching it up, and using the true power of our animal brain, pattern matching. Mm-hmm. So, everybody of us has a nice little thing called the brain, and it's really good at pattern matching, visual pattern matching. They can recognize patterns easily. So we have done that. And then my brain was trained to actually recognize this problem. I don't know why. And basically, I work with a statistician, Andreas Madsen, a Node core collaborator, to actually codify this in some ER files that were translated then to Node, so that we could create some recommendations out of for this. What does it come the recommendation to? It says, typically it says how to mitigate the problem, but more importantly, what tool to use next to actually diagnose what's happening. So for example, here, this is the output of Clinic Doctor. It generates this nice diagram. It monitors CPU usage, memory usage, the event loop delay, and the usage of resources. And what you can see here is that the CPU is low, but it has big spikes. So this typically means that you have an I/O issue, because you have a long time of nothing happening, and then you have a big spike, like CPU now is going. Is ticking, so it's waiting some long-running I/O activity down there. Then, the other thing, with this type of thing, it will recommend BubbleProf, which is the tool for debugging I/O, for profiling I/O activity, that I will speak about it later on. But if you have an event loop delay problem, or
In which case, this graph would go red.
This go red, you will use Clinic Flame.
So a Clinic Flame collects metrics by CPU sampling. If anyone's heard of 0x, it's essentially based on 0x. It tracks top of stack frequency. So for every, say, millisecond slice that you're taking off the CPU to see what the stack is, there's always going to be the last function called on that stack. It doesn't necessarily mean the last function that's called in that whole function stack in the program, but it will be the last function that has been called for that sample. So taken over time, if a function appears at the top of the stack more times in ratio to other functions, then you can consider that function hot. You can consider it that it's blocking the event loop. And so it takes these metrics and it creates a visualization called flame graphs, which you might have heard of. So here's an example flame graph, and that is bright as the sun. We can see that there's red stacks here, and the redness, the hue from sort of a peachy color to a darker sort of red, the redness illustrates the top of stackness of a function. So again, we can use the nice little thing, as Matteo put it, called our brain, our animal brain, to use very quick pattern matching. In here we can see these are the red things, these are the things that we need to investigate. And again, we're going to go more into that shortly. And then if this is for an internal bottleneck, so this is to find something internally in your process that's the bottleneck. However, in the case of external bottlenecks, we have BubbleProf.
So BubbleProf is a new tool based on async hooks from Node Core. So it uses this new feature introduced in Node 8 that's called async hooks that enable us to track latency between all the various asynchronous operations. And it creates this new visualization called a bubble graph, which is pretty new. This tool is not released yet. It will be released later on this month. There was a little bit of a mishap, but sorry. And it will be open source later on. So this is the visualization. It's pretty novel. This has never been tried that we know of. And what you can see here on the right, you can see that we show a diagram of the asynchronous operations that we can see on your process. So you can see that we have 781 calls, asynchronous calls being done. And over here, you can see that we have some big bubbles, and you can click it through, and we'll show this later on. But these can be clicked and expanded, and these represent a tight group of asynchronous activities that happens together. And then we have a big delay, and then another tight group of activities that happen, and they can be both synchronous and asynchronous.
So the bigger the bubble, the more time was spent doing things.
Yes. And
the longer the line, the longer the wait.
Yes. So this is, as I said, this is going to be released later this month. The documentation is not finished, so that's why.
But if you, in a second, when we do the live demo, you can load a web page where you can actually play with this on your laptop as well.
So you can try it out. So now it's time to ask one question.
And the question is, where is the bottleneck? Which is the question that we've already asked. So to find the bottleneck, you can use Doctor. And Doctor will be able to indicate to you whether you're dealing with an internal bottleneck, say if the event loop's blocked, or an external bottleneck, say you have an I/O problem. So once you've determined using Doctor whether it's internal or external, you can use Clinic Flame for internal bottlenecks, you can use BubbleProf for external bottlenecks. And we're going to show you all that right now with a good old-fashioned live hack. If you want to follow along, or sorry, if you want to interact with the demos, go to nf.ie/interact. Maybe not on phones. This is mostly built for Chrome, most of this stuff. There's also a feedback form if you like, it would really help us out if you like to give us your feedback. We'd really appreciate it. So, without further ado, here we go. So, what Matteo is going to do is he's going to run a server, and he's going to establish a baseline. So the first thing he's doing is opening the server, and he's going to use autocannon, which we mentioned earlier, to put some load on the server, simulate some load, and see how many requests per second we're going to get, and see if that's good. And whether it's good or not, obviously, is context dependent. However, I think maybe 2.6 requests per second in most contexts isn't very good. So what we're going to do then is go and we need to establish where is the bottleneck. So we ask Doctor. So clinic Doctor is using an on-port flag here, which will basically run this command when the process opens a port. So it's going to -- and then node process. And what the on-port flag does as well is it injects the first port that the process opens in as that port variable. Okay, so now it shows us what we were looking at earlier. Wow, that looks so good this big. Is that it's detected a potential I/O issue. We have big CPU spikes and then big troughs, which indicates that something is not quite right. There's a recommendations panel down the bottom. When we release BubbleProf, currently this says to the best way to deal with this is to think about your infrastructure. So it's not the best recommendation. I did the best I could. There's quite a lot of text in there, like trying to talk you through what to do. But as soon as we release BubbleProf, we're going to update this to say use BubbleProf.
There is a lot of text.
Yeah, I wrote the recommendation stuff. What we have to do is use BubbleProf, and the command is exactly the same, except you replace Doctor with Bubble. So again, once the port's opened, it uses autocannon. We're only using 2 connections currently, because clearly it's not going to be able to manage much more than that. And then it generates this visualization. And if you've gone to nf.ie/interact, you can actually click BubbleProf View to see this visualization and play with it yourself as well.
So one of the things you can do with this visualization is you can see that there is a lot of time spent in Mongo. Okay, you can see this. You have this line on Mongo.js cursor. So if you click about this line of Mongo.js cursor, you can see that there are 2 trunks of this. And if you click on one of those trunks, you can see that we collect all the frames of your application, by the way.
So this first trunk is spending almost 6 seconds doing asynchronous things.
And just 38
out of the 10 seconds that have been sampled.
Only 38 seconds of milliseconds of synchronous execution. But the most important thing that this tells you is this specific part, which I want to highlight. It tells you exactly the line of code in your app where this action has been triggered. So we can collect that exact point. So let's go and look at that line in my file.
So Matteo's going to open 1.js, go to line, whoa, what's going on there? Go to line 11, and what we can see is we're doing a sort operation with Mongo. There's also another one on, after a find, there's also another one on column 13, which is, as Matteo's going to show us, that second line, which takes up another, how many seconds is that? Like 5 seconds?
Another 5 seconds.
And again, shows us where that second asynchronous operation is triggered. So in total, there's like 9.8 seconds that's spent doing asynchronous work out of 10 seconds, which doesn't seem right.
Yeah.
So go ahead, Matteo, tell them what you're doing.
Yeah, no, you tell. Oh, I'm telling you. Yeah.
Yeah, you do this bit.
Yeah. So what I'm going to do now is I'm going to ask Mongo what is going wrong with that query. So I go to my database. By the way, this is querying all of NPM data. So, just saying you can pull that out.
So this is great because this is where you go outside. This is where it's leading you outside of the node process to find that bottleneck. And this is where other skills come in. You might need to work with other people or whatever, but in our case, we can actually just open up the Mongo CLI and play around.
It's very nice to use, very simple to use. You can copy and paste the same syntax. You can see it at the bottom. We are getting the modules collection using find, sort, limit 5. This is the query. You can see it takes a while to respond, right? It's just
it's not super fast.
Mongo has this nice command called explain. And if you're using Postgres and so on, they also have the same type of comments. Now, what you can see here is that the thing this is going to do, the query plan that your database is going to use is it will just sort the whole collection every time, which is, considering the amount that there are 500,000 modules on NPM, is pretty fast, okay? But it's still very slow to do for every request. So, what it is if you have, I did some fair amount of this type of work in the past. And I'm actually like, well, maybe this needs an index. So I don't know. Maybe there is something else in this database that I can use.
Oh, I do wonder.
So you can, let's query, oh, but there is a modules indexed collection.
What serendipity?
That's serendipity, right? So we are running this now, and with the same query, with the different...
Exact same query.
The exact same query with a different collection. In fact, you can see that now it's using an index scan instead, which is way faster than just doing a full sort every time. Hey! How come?
So we're going to go update the code, or actually go to code that we prepared earlier.
And we just swap the collection to the new one, same code.
Modules to modules indexed. And now let's see whether that fixes the problem. Should be nice and fast now. So Matteo's going to run another, we've done an optimization, so now we're going to establish a new baseline and see what improvement we have. So remember before it was 2.5 milliseconds, now it's 2.5 requests a second. Now it's 80 requests per second. That's better, but I think we can do better, Matteo.
Really?
I do think so. Why don't we run Doctor again and see what it says? So you can see that this actually can become quite a sort of easy. That's number one. You need it on two.
We need to do one more thing, Dave. You forgot. So one thing we need to do now, given that we can run a little bit faster than before, so maybe the database won't
show. Oh, that's right. Let's try and use more connections.
We can actually try to put some more load to the system because we're just eating it with two concurrent connections. So that might be the problem. That led to 80 requests per second. Yeah. So we might want to increase the number of load because given that we have removed a serious bottleneck, we might want to try with a bigger volume, bigger load. So maybe that is the problem. Maybe. Let's see how this will come out.
Suspense. Okay, slightly faster, but still not great. So the next thing we're going to do is we're going to do another health check with Doctor with 100 connections. And as you can see, it's quite habitual now. It really just becomes like quite small edits. And it's the same when you use Doctor, whether you use Bubble, whether you use Flame. It's all the same. Okay, surprise, surprise. By solving the asynchronous issue, the external bottleneck, we've now revealed an internal bottleneck. How cool. What awesome person came up with this example code?
It was not me, by the way, it was Matteo.
It was Matteo. So in the recommendations, it will tell us to use Clinic Flame to discover CPU-intensive function calls. So that's exactly what we're going to do. So essentially, again, same exact command, except you replace Doctor with Flame. And again, it's running the process. It's using the on-port coolness. And then hopefully, Flame's going to show us, the Flame graph is going to visualize where the problem area is. And again, goodbye eyesight. So in this, we won't stay on here too long, but we can see that in every case, we have a red stack that's called compute magic. That seems suspicious to me. That's on line 25, column 23. So Matteo's going to open that up, go to line 25. Oh, look, some really interesting code. I have no idea what you were thinking when you did this. I don't know. Were you taking magic mushrooms, and that's why you called it compute magic? I mean, but it's funny how much you find really useless slow code in real systems. So we don't actually need any of that, Matteo. I have no idea why you did that. So what we're going to do is we're just going to remove that function and see if that helps. I wonder if it will. So, optimized, and now we're going to get a new baseline. So it went from 2.5 to, say, 90, and now 1,380. That's quite a big jump. Is that the end?
No, we have one more step, man.
Oh, okay. And what's the... Oh, we're going to... So, well, let's see if Doctor can... if there's anything else to see. Any other health checks? 9, 10. Whoa, okay, so doctor says it's healthy. Doesn't mean it's definitely always healthy, but we have a nice validation that we've probably reached a place where this is good enough. So in the words of Shaggy, it wasn't me.
It wasn't me. In fact, it was the work of a team. So, in frankness, it's from time to time some people forget that it's us presenting it, but there's a lot of people working on the stuff. I want to thank Andreas Madsen, a Node Core collaborator, Joy, Connor, our designer, Connor, our chief product officer. I'm not thanking myself. Matthias.
Thank you, Matteo.
Thank you. Matthias Boos, mad scientist. Alan Slater, our UI
guy.
UI UX developer that did the BubbleProf visualization. Camille Mack, our full stack developer. And I would thank David Mark Clements that did the 0x and frame ref thingy.
Oh, thank you.
And with that, would you like to have some parting words?
Yes, and we definitely go over time.
You can clap again, it's fine. Set quantifiable performance goals.
So, remember that whenever you start doing some performance work, you should check with your manager and your product owners what are the business requirements. If you don't do that, you might go into a rabbit hole. So make sure that you check that, because this is very important. Because you might not have all the context.
Mm-hmm. Choose fast libraries, because if you do a bit of research and you find libraries that are already fast, when it comes to optimizing code, you've got a much higher chance of optimizing your own code than optimizing the code of your dependencies. Sarah and I wrote Pinot, which is a high-speed logging library, and Matteo has been involved in Fastify. We've got Thomas, massive contributor to Fastify. It's a really, really fast high-speed web framework. I recommend that. Of course, there's many others out there, but those are the ones that we are involved in. And then finally, beware of the rabbit hole. Sometimes 80% of the effort is like the final 20% of optimization. You really need to answer the question, is this worth my time now? Because at a certain point you reach diminishing returns when it comes to optimization work. And if you allow yourself, you can get lost in that and actually you end up costing more money than you're saving. So it's really important to find out what fast enough is for your context and remember to balance the cost.
Finally, it's perfectly fine to write slow code. And you don't always have to reach
ludicrous. Do it again.
You don't always have to reach
ludicrous speed. There we go. Thank you. If you get a chance to share this in really appreciate it. Make us feel better about it. It's nice to have feedback.
Yeah, it's
CBFB.
Also remember, thank Mia for doing all of this and sponsor all of this work. And please come talk to us if you have any questions around all of this. If you need help about Node.js, if you need a job, whatever. Get here.